Having understood the relevant fundamental theories and the very basic instrumentation from the previous lectures, we now turn to look into the basics of two classic electrochemical techniques, chronoamperometry and cyclic voltammetry. For both methods, the potential of the working electrode is controlled in a predetermined way as a function of time using a potentiostat, and the resulting current is recorded as a function of time or potential. In the following, we will see the well-established correlation between experimental parameters and the fundamental kinetic parameters. As such, these potential-controlled methods are considered as the most powerful approaches available to fundamental electrochemistry. And more specifically, I will introduce the chronoamperometry of only the solution phase species at both macro and microelectrodes, while for cyclic voltammetry, I will very briefly describe the theories for both solution phase and adsorbed species at both macro and microelectrodes. Please also note that all the discussions in this lecture are limited to first stationary disk electrodes in a stationary solution, which means we only consider the electrodes with the two-dimensional disk geometry for their electroactive part, and diffusion as the sole way of mass transport of the solution phase species. And second, solutions with a constant bulk concentration, which simply requires the solution has a large enough volume. The simplest way of varying an electrode potential is to apply a single potential step. Chronoamperometry is such a potential step method. As shown in Figure A, the electrode potential starts with E1 where no reactions occurs, and then abruptly increases to E2 where the reaction of interest is driven so hard that the rate of electron transfer is limited by the rate of mass transport. The resulting current density is plotted as a function of time in Figure B. We first look at the red curve, which is for capacitive current, and it occurs in every time, but only for the first tens of milliseconds. And then due to the selection of potential E2, the Faraday current is controlled by the diffusion of the reaction species from the bulk solution towards the electrode surface. For a disk electrode, the diffusion-limited current can be fully expressed by the equation 4 times n, the number of electrons transferred, F, the Faraday constant, C star, the bulk concentration of the species, D, the diffusion coefficient, and Re, the electrode radius, times F tau, function of dimensionless time tau, where tau equals to 4dt divided by Re squared, or can be written as square root of 4dt divided by Re squared. So the dimensionless time can be understood as the ratio of the diffusion layer thickness to the electrode dimension. And calculations have been made to show that if tau is far smaller than 1, then f tau is approaching pi over 4 tau square root, and if tau is far larger than 1, then the value approaches 1, a constant. So then apparently we can see that the magnitude of the diffusion-controlled current would largely depend on how far the diffusion layer has evolved relative to the electrode dimension. Therefore, it's important to consider two limiting cases. One is in the macroelectrode limit, and the other is in the microelectrode limit. For a macro disk electrode, its radius is large compared to the diffusion layer thickness at any time, so tau much smaller than 1 always holds, and this corresponds to a linear diffusion regime, as depicted in the upper inset in Figure B. And consequently, we would have the Faraday current equal to NFA square root of d times c star divided by pi t. And this is exactly quaternion equation, which is shown by the green curve in figure B. And figure C combines both contributions from the capacitive current and the Faraday current, such that when the capacitive current completely decays to zero, the current time response would be fully quaternion. Nevertheless, the natural convection would operate after 20 or 30 seconds, and the current will approach a steady state. In the microelectrode limit, tau much smaller than 1 is also true, but only for the first tenths of millisecond in most cases. But unfortunately, this part of Faraday current would overlap with the capacitive current. Then tau much bigger than 1 would soon later operate, because at this time the diffusion layer expands rapidly relative to the electrode dimension, so the diffusion layer thickness may soon exceed the electrode dimension, and at this time the edge of the disk becomes significant and the convergent diffusion regime operates, which is depicted in the lower inset in figure B. And the Faraday current is found to be 4NF C star D RE, which is the steady state current. Similarly, combining both contributions of Faraday and non-Faraday processes, we have figure D. And when the capacitive current completely decays to zero, we have the steady state current all the time later on. The current time response we get from a chronoamperometry is very useful for studying a reaction system, because we know the current we get is a function of number of electron transferred and the bulk concentration as well as the diffusion coefficient. So as long as we know two of the three quantities, we can derive the third one. And in particular, if we know the bulk concentration and the diffusion coefficient of the reaction species, then we can know the number of electrons transferred during the elemental process. And this would be very useful for probing the unknown reaction mechanism. The inherent simplicity of the potential control in the chronoamperometry limits its applications. Another method of cyclic voltammetry controls the potential in a more complex way and are therefore able to afford significantly more insights into the reaction systems, especially regarding the electrogenerated species and the electroactive intermediates. Specifically, this method applies potential sweeps as a function of time, as shown in the figure here. The electrode potential starts from E1, where there is no reaction, and then is varied at the scan rate of V, which is equal to the step size divided by the step duration. And the way the potential increases resembles a staircase, where every step is the same. For this forward potential ramp, the potential finally reaches a value of E2, which is already sufficiently oxidizing or reducing to drive the reaction of interest. And any potential in between can be expressed as E1 plus Vt. More precisely, the step size should ideally be infinitely small. Nevertheless, in practice is often smaller than 1 millivolt, which is good enough for most current research. Then we look into the current generated within each step duration. As learned from the last section, there are two contributions for the current from both the Faraday process and the non-Faraday electrode double layer charging. And because the step duration is usually very short, so the capacitive current and the Faraday current almost overlap all the time. So if now we plot the total current as a function of potentials applied, including the backward potential sweep, it will look like this. And apparently this is far too complex to analyze, and actually we are only interested in the Faraday current. Well, studies have been made to show if we sample the current during each step at the 30% of the interval, more or less here, the final current is consistent with what we predicted from theory for the Faraday process. As such, we sample the current for each step at alpha equals to 0.3, and alpha is the sampling factor, and then plot it as a function of potential. We would have a curve like this, and this looks very much like a typical cyclic voltammogram. To understand the shape of this curve from a molecular level, let's consider a consistent electrode system for the graph. That is, a reversible solution phase reaction using a macroelectrode. It is now important to be reminded that the sign of the current does not mean the magnitude of the current. And by IUPAC recommendation, the negative sign for the current means the reduction current, and the positive sign for the current means oxidation current. So based on this convention, we can see from the graph here, the potential sweep must start from 0.2 as the current equals to 0, and then first experience a reduction. So if we assume the electrode reaction is O plus E in equilibrium with R, we know that initially, before any potential sweep, only species O is present in the solution. Then we divide the forward curve into 4 stages. First, there is no current, and second, the current starts to rise, and third, the current reaches the maximum, and fourth, the current is dropping. And apparently for stage 1, even if there is a lot of species O, the potential is not reduced enough, so there is no reduction at all. And then in stage 2, the potential becomes sufficiently reducing, so the reduction starts. And between stages 2 and 3, there is enough materials at the surface and the potential keep increasing, so the consumption rate of O by the interfacial electron transfer is increasing, such that we can see an increase in the current. And meanwhile, the diffusion layer keeps expanding, so the rate of supply of the material by the diffusion keeps decreasing. And at the peak potential, the rates of supply and consumption of the materials equals to each other. However, at stage 4, although the rate of interfacial electron transfer still keeps increasing, but the supply of the material by diffusion also keeps decreasing, and that means there is simply not enough materials. As such, the current keeps decreasing in this stage. Then for the reverse sweep, we can also divide it into the 4 different stages, and it's basically the same as the reduction process, the same as above, but it's just for the oxidation of electrode-generated species R to O. From the Compton just above, we can see that the shape of cyclic voltammogram is dictated by the kinetics of the rate-determining step, or whichever step is slower. For simplest solution phase reaction, there are always 2 competing processes of interfacial electron transfer and diffusion. One is for the consumption of the materials at the electrode surface, and the other is for the supply of the materials from the bulk solution to the electrode surface. It will be easier to understand the following discussion if we draw the current plot as a function of time or potential. For the cyclic voltammetry, well, these 2 quantities are linearly dependent on each other, so it doesn't matter if this axis is t or e. Then for the interfacial electron transfer, the current would always increase exponentially as a function of potential or time, as seen from the Batchelor-Voltammetric equation that the current is proportional to the e to the power of e. However, the diffusion-controlled current will keep decreasing, as we see from the last section that the current is inversely proportional to the square root of time. Then we connect the current of the rate determining steps, which is the lower step, and then we can see there's a peak formed of the current. However, unlike the monotonous change of the electrokinetics with electropotential, the trend in the diffusion-controlled current may look very different depending on the electrode dimensions. The curve I just drew for the diffusion-controlled current is for the macroelectrode, where linear diffusion regime operates. But for the electrode with tiny dimensions, the diffusion-controlled current may drop dramatically and soon reach a steady state. And this is for microelectrode, where for the most of the time, the convergent mode of diffusion operates. In this case, we see no peak of the current. So it's now important to compare the relative time scale of the time required to reach the steady state, and second, the voltammetric time scale, TCV, and the TSS is roughly RE squared divided by D, and TCV is roughly RT divided by FV. Then we can introduce a parameter P, which combines the two quantities as the square root of the ratio of the two time scale, which further equals to FRE squared. And for the macroelectrode limit, because the voltammetric timescale is always short compared to that required to reach the steady state, we would have P much bigger than 1 always holds. And conversely, for microelectrode, because the diffusion-controlled current reaches steady state so soon that we can always observe it during the voltammetric timescale, and therefore P is much smaller than 1. And therefore in the following I will describe the characteristics of different cyclic voltammograms separately in the macroelectrode and microelectrode limits. We first discuss the cyclic voltammetry of a solution phase reaction at a macroelectrode surface. The characterization of macroelectrode voltammetry is based on the reversibility of the electrochemical behavior of the redox couple. Reversible voltammetry here means a fast electrode kinetics, where the redox couple appears always at the equilibrium. So the system can be described by thermodynamics. For example, the concentration ratio of the redox couple can be described by the Nernst equation. On the contrary, irreversible voltammetry refers to the slow electrode kinetics, and the system appears not at the equilibrium all the time. However, fast and slow is termed relative to the diffusional mass transport, and we have the corresponding rate constant for these two core processes, K0 and mass transport coefficient. They have the same unit, so they can be directly compared. The standard electrochemical rate constant is intrinsic to specific reaction system and does not depend on any experimental parameter, but the mass transport coefficient equals to the diffusion coefficient divided by the diffusion layer thickness. And from last lecture we know that the diffusion layer thickness is roughly square root of dt, and the voltammetric timescale is roughly RT divided by FV, be the scan rate, such that we have the equation further equal to the square root of dFB divided by RT. And then we can introduce a diagnostic parameter lambda equals to K0 divided by mt, which is simply the combination of the equation. Specifically, when lambda is bigger than 10, the system is considered to be a reversible system if it's in between 10 to the power of minus 3 and 10, then it's a quasi-reversible system. But if it's smaller than 10 to the minus 3, then it's considered as an irreversible reaction system. And notably, we can see the parameter lambda largely depends on the voltage scan rate. It is now important to critically think about the reversibility of the reaction system, because when the applied voltage scan rate is extremely large, say 1000 volt per second, which is easily achievable with the current technique, then basically all currently known system will appear irreversible, because so far the known fastest electrode kinetics only has a K0 value of 10 cm per second. And conversely, it's also true if the applied voltage scan rate is extremely small, then all these systems would appear reversible. Therefore, it's always important to report the voltage scan rate you used in your experiment when you do such an analysis. Then we move on to discuss the characteristics of reversible and irreversible voltammogram. And we will not include the quasi-reversible case because it's not so well defined. Oh, and corresponding to this graph, the reaction we are considering here is the oxidation rather than the reduction discussed in last slide. So the reaction here is R minus E in equilibrium with O. And we consider the reversible case and irreversible case. And I will discuss the characteristics in terms of peak current, peak-peak separation in terms of potential, and midpoint potential. Okay, let's draw the box. In the reversible limit, the peak current is, and in the irreversible limit, it's slightly different. We can see the two peak currents are only different at the very beginning. And because beta, the transfer coefficient, is usually 0.5, so if all the other quantities are the same, the irreversible peak current is always slightly smaller than that of the reversible case. For the peak-peak separation, a reversible one-electron transfer process always has a value of 57 millivolt, and the peak separation of an irreversible system is proportional to the logarithm of voltage scan rate, as it equals to 59 divided by beta times log 10 scan rate plus a constant C. And the midpoint potential, regardless of the voltage scan rate and the reversibility of the system, is always the standard formal potential as long as the diffusion coefficient of the two species are equal. Then let's look at the microelectrode limit. We can see the voltammograms looks vastly different from that in the macroelectrode limit, because on a microelectrode surface with a very small electrode radius, the diffusion layer expands very quickly even over the electrode dimension and has a convergent diffusion mode. So the diffusion-controlled current quickly enters a steady state, and therefore we don't see the formation of a peak. And also strikingly, because the diffusion is so fast, upon oxidation, any species O formed will be quickly removed from the electrode surface, and therefore we are not able to see the reduction of it. So in the voltammogram, we only see the oxidation current. Then to discuss the characteristics of the voltammetry of different reversibility, we also need to compare the two parameters, K0 versus MT, which is again d over delta. But this time the diffusion layer thickness is in a similar magnitude with the electrode radius. So we introduce another diagnostic parameter, kappa, which is again equals to K0 divided by MT, which is further RE K0 divided by D. And similarly, empirically, when kappa is bigger than 10, the system is deemed as reversible, and if it's in between 10 to the power of minus 2 beta and 10, it is quasi-reversible, and if it's smaller than 10 to the power of minus 2 beta, then it is irreversible. Then again, we discuss the characteristics of microelectrode voltammetry in the reversible and irreversible limit. So for the same equilibrium, we discuss in terms of steady state current, and there's no peak-peak separation and also no midpoint potential. But here, the same symbol means the half-wave potential. Then we must notice that the steady-state current is independent of the reversibility of the system, and this can be understood because the steady-state current is a diffusion-limited current, which is only controlled by the lowest diffusion layer thickness, and this diffusion layer thickness is only dictated by the electrode dimension, not upon any properties of the molecular systems. The independent of the magnitude of steady-state current on the reversibility of the reaction system can also be seen from its equation, which we also learned, for an Fd concentration of R and the electrode radius. And the half-wave potential in the reversible limit is exactly the standard formal potential, and in the irreversible limit is the standard formal potential plus RT divided by beta F times ln K0 RE divided by D, which is kappa, basically. And we also need to assume the diffusion coefficient of the two species are the same. And remember, this symbol is half-wave potential, but the symbol here is the midpoint potential. Alright, now the characteristics of different voltammetry, of different reversibility, and how the reversibility is charged based on the diagnostic parameters, and all of this should be clear now. All the discussion before in this lecture is only for solution phase reaction. However, adsorption of reaction species is not uncommon. Let's consider an ideal case of one-electron oxidation, R AD minus E in equilibrium with O AD. And the bracket AD here means the adsorbed state of the reaction species on the electrode surface. Then to account for the ideality of the case, we need a few assumptions. First, all the adsorption sites are equivalent. And second, there is no interactions between the adsorbed species. And third, the surface activity is equivalent to the surface coverage. And fourth, the surface coverage is independent of the applied electrode potential. Only with these assumptions we can think the electrode reaction as an ideal reaction. As such, the resultant voltammogram would have well-defined parameters, as can be seen from the symmetry of the voltammograms shown in this figure. Actually, in many cases, regardless of the ideality of the reaction, the rate of the overall reaction may be dominated by the finite amount of the adsorbed species, and therefore in the voltammogram we wouldn't see a diffusional tail. So that's why these voltammograms looks hugely different from that of the solution phase reaction. Furthermore, the shape of the cyclic voltammogram is solely determined by the rate of the interfacial electron transfer and its reversibility. Then we can easily understand the shape of these voltammograms regardless of its reversibility, where initially abundant adsorbed species are present on the electrode surface, and then the point electrode polarization. So more and more species R is being oxidized. Then at the potential where the concentration of the species becomes so low that the overall electron transfer rate starts to drop despite the increasing oxidation rate constant. As such, a peak forms. And eventually, because all the adsorbed species are depleted, the current decreases to zero. On the reverse scan, the same processes happen to the oxidized species O. The voltammogram of the ideally adsorbed species is mainly characterized by its peak potential and peak current. So we draw the box for the one electron oxidation, include peak potential and peak current, reversible and irreversible boundary lines. The major difference between the reversible and irreversible cases is the peak potential. In the reversible limit, both oxidation and reduction peaks are at standard formal potential. And in the irreversible limit, the peak potential equals to the standard formal potential plus or minus RT over beta F times ln beta FV divided by RT K0. Oops, the box is not long enough. The peak current is given by the equation for the reversible limit. The tau total is the total surface coverage or activity. And for the irreversible limit, it's slightly different. Now we should notice that for both reversible and irreversible limits, the peak current is always directly proportional to the scan rate. And this is different from the solution phase reaction. The peak current is always proportional to the square root of the scan rate in these two limits. And this difference is very important because it can be used for distinguishing whether an unknown reaction is a surface reaction or a solution phase reaction.